Wi-Fi 1. Wi-Fi 1, officially known as 802.11b, launched in 1999 and marked the first time wireless internet became practical for everyday people. Before this, connecting to the internet meant dealing with cables, which limited where you could use your computer. Wi-Fi 1 operated exclusively on the 2.4 GHz frequency band and delivered maximum speeds of 11 megabits per second. To put that in perspective, this was enough for basic web browsing and sending emails, but streaming a video or downloading large files would have tested your patience significantly. The 2.4 GHz band came with a frustrating problem that users quickly discovered. This frequency range was already crowded with other household devices. Cordless phones, microwave ovens, baby monitors, and even Bluetooth devices all transmitted signals on the same 2.4 GHz frequency. Every time someone heated up leftovers in the microwave or made a phone call, the Wi-Fi signal could get interrupted or weakened. Imagine trying to load a web page while someone is nuking their lunch, only to watch your connection drop completely. Delightful. The slow speeds created another limitation. With only 11 megabits per second available, only 1 or 2 people could realistically use the network at the same time. If multiple users tried connecting simultaneously, the already sluggish connection became unbearably slow and unresponsive. This meant households had to take turns using the internet, which explains why many people still preferred wired Ethernet connections. At least with a cable, nobody could accidentally disconnect you by reheating coffee. Wi-Fi 1 proved that wireless internet could work, but it also showed there was substantial room for improvement in both speed and reliability. Wi-Fi 2. Wi-Fi 2, officially designated as 802.11a, also arrived in 1999 alongside Wi-Fi 1, but it took a completely different approach to solving the wireless internet problem. Instead of using the crowded 2.4 GHz band, Wi-Fi 2 operated on the 5 GHz frequency band. This higher frequency allowed it to deliver speeds up to 54 megabits per second, which was nearly 5 times faster than Wi-Fi 1. Suddenly, downloading files became quicker and web pages loaded much more smoothly. For 1999, this was genuinely impressive performance. The 5 GHz band offered a major advantage beyond just speed. Because most household devices only emitted signals at 2.4 GHz, the 5 GHz band remained relatively empty and peaceful. This meant Wi-Fi 2 experienced significantly less interference from microwaves, cordless phones, and other electronic devices. The connection remained stable and consistent, which made it ideal for environments where reliability mattered more than anything else. Offices and businesses particularly appreciated this stability, even if it cost more than Wi-Fi 1 equipment. However, Wi-Fi 2 came with a significant trade-off that limited its adoption. The 5 GHz signal had a much shorter range than 2.4 GHz. Higher frequency signals struggled to penetrate solid objects like walls, floors, and furniture. This meant Wi-Fi 2 worked beautifully if you stayed close to the router, but the signal weakened dramatically as you moved away or into different rooms. Because of this limitation, Wi-Fi 2 was primarily deployed in office buildings and corporate environments where multiple access points could be installed throughout the space. For home users who wanted coverage throughout their entire house, the short range made Wi-Fi 2 impractical. You could have blazing fast internet in one room and absolutely nothing in the next room. Not exactly the wireless freedom people were hoping for. Wi-Fi 3. Wi-Fi 3, officially known as 802.11g, launched in 2003 and became the generation that finally made wireless internet popular with regular consumers. The engineers behind this standard realized they needed to combine the best features from the previous 2 generations while eliminating their weaknesses. Wi-Fi 3 accomplished this by returning to the 2.4 GHz frequency band like Wi-Fi 1, but now it could reach speeds up to 54 megabits per second, matching the performance of Wi-Fi 2. This combination turned out to be exactly what people needed. The real genius of Wi-Fi 3 was solving the fundamental problem that plagued earlier standards. Wi-Fi 1 could cover a wide area throughout your home, but the speeds were painfully slow. Wi-Fi 2 delivered excellent speeds, but the coverage area was so limited that you practically needed to sit next to the router. Wi-Fi 3 gave users both decent speed and wide coverage at the same time. You could finally walk around your entire house while staying connected to the internet at reasonable speeds. Revolutionary stuff, apparently. Another crucial feature made Wi-Fi 3 even more appealing to consumers. It maintained backward compatibility with Wi-Fi 1 devices, meaning older equipment could still still connect to Wi-Fi 3 routers without any issues. This was important because people had already invested in Wi-Fi 1 devices and were not thrilled about replacing everything. The combination of better performance, good coverage, and compatibility with existing devices made Wi-Fi 3 routers extremely popular. By the mid-2000s, Wi-Fi 3 became common in homes and small businesses everywhere, enabling smoother web browsing, faster file downloads, and easier connectivity between computers, printers, and the early smartphones that were just starting to appear. This was the generation that convinced most people that wireless internet was actually worth using, instead of just a frustrating experiment. Wi-Fi 4. Wi-Fi 4, officially designated as 802.11n, arrived in 2009 and represented the first major breakthrough in wireless technology. This generation introduced dual-band support, which meant routers could now transmit both 2.4 GHz and 5 GHz signals simultaneously. This was a game changer because users could finally choose which frequency band to connect to based on their specific needs at any given moment. The maximum speeds also increased dramatically, reaching up to 300 megabits per second on the 2.4 GHz band and up to 600 megabits per second on the 5 GHz band. The way dual-band functionality worked in practice was straightforward. When you looked at available networks on your device, you would typically see two networks with similar names, both coming from the same router. One network used the 2.4 GHz band and the other used 5 GHz. Let's say your router was located on the second floor of your house. If you went downstairs to the first floor, your phone could stay connected using the 2.4 GHz signal because it had a wider range, even though the speeds were slower. But when you wanted to download games or stream high-definition videos, you could move back upstairs near the router and switch to the 5 GHz network, which offered faster speeds and minimal interference from other devices. Finally, some flexibility. Wi-Fi 4 also introduced a technology called MIMO, which stands for multiple input, multiple output. Before MIMO existed, routers sent and received data one stream at a time, which created delays as the router processed information sequentially. With MIMO technology, the router could send and receive data continuously and simultaneously using multiple antennas. This resulted in faster and more consistent connections overall. Wi-Fi 4 became the backbone of wireless networking for nearly a decade, and many devices and routers from this era remained in use for years because the performance was finally good enough for most everyday tasks. Wi-Fi 5. Wi-Fi 5, officially known as 802.11 AC, launched in 2013 and became the first Wi-Fi generation to reach gigabit-level speeds. This standard operated exclusively on the 5 GHz band and could deliver maximum speeds up to 3.5 gigabits per second under ideal conditions. This massive speed increase made activities like streaming 4K videos and downloading massive files, such as AAA video games, significantly smoother and faster. For the first time, wireless internet felt genuinely fast rather than just acceptable. Wi-Fi 5 introduced a feature called MUMIMO, which stands for multi-user, multiple input, multiple output. This was essentially MIMO technology, but designed specifically for handling multiple users simultaneously. Before Wi-Fi 5, routers could only send data to one device at a time, which meant all other connected devices had to wait their turn. If you had several people in your household trying to stream videos, download files, or browse the web at the same time, everyone experienced slowdowns as the router struggled to serve each device sequentially. With MUMIMO, the router could send data to multiple devices simultaneously, so downloading or streaming on many devices could stay smooth at the same time. No more fighting over bandwidth. Wi-Fi 5 also featured a technology called beamforming, which changed how routers transmitted signals. Normally, Wi-Fi signals spread out in every direction equally, like a light bulb illuminating an entire room. This meant a lot of that signal got wasted, sending data in directions where no devices existed. With beamforming, the router could focus the signal directly toward your specific device, creating a stronger and more stable connection, especially when you were positioned far from the router. However, despite all these speed upgrades and fancy features, the actual performance you experienced still depended entirely on the internet plan you purchased from your internet service provider. These numbers represented the maximum capability of the router itself. If you owned a Wi-Fi 5 router but only subscribed to a 100 megabits per second plan, you would still only get 100 megabits per second, not multiple gigabits. The router was not magic. Wi-Fi 6 and Wi-Fi 6E. Wi-Fi 6, officially designated as 802.11 AX, was released in 2019 with a specific design goal in mind, handling many devices simultaneously without performance degradation. It operated operated on both the 2.4 GHz and 5 GHz bands, with maximum speeds reaching up to 9.6 gigabits per second. However, what truly made Wi-Fi 6 exceptional for large-scale use was not the raw speed increase, but rather a new feature called OFDMA, which stands for Orthogonal Frequency Division Multiple Access. This technology made routers perform more efficiently when connected to numerous devices, ensuring that speeds remained fast, even under heavy load conditions. OFDMA worked by dividing wireless channels into smaller sub-channels, allowing the router to serve multiple devices efficiently at the same time. Unlike Wi-Fi 5, which had MU-MIMO with only 4 simultaneous data streams, Wi-Fi 6 supported up to 8 simultaneous data streams. This improvement made Wi-Fi 6 routers particularly popular in environments like cafes, airports, large offices, and homes with many connected devices. Everyone could maintain solid performance without experiencing the congestion issues that plagued earlier standards. Additionally, OFDMA helped reduce latency significantly, which made Wi-Fi 6 excellent for competitive online gaming and video calls, both of which require fast real-time responses without lag or delay. In 2021, Wi-Fi 6E arrived as an extension of Wi-Fi 6, bringing access to a brand new frequency band, 6 GHz. This additional spectrum proved extremely useful in environments like corporate offices and professional studios where hundreds of devices were already using the same 2.4 and 5 GHz bands from multiple routers. All those overlapping signals created interference and instability. The 6 GHz band provided a clean, uncongested space where devices could operate without interference from existing networks. However, not all devices supported Wi-Fi 6E immediately. Usually only high-end flagship devices like recent iPhones, MacBooks, Samsung Galaxy Ultra series phones, and gaming laptops from manufacturers like Asus ROG could take advantage of this new band. Many Wi-Fi 6E systems also utilized mesh networking, which deployed multiple small routers around a building to create one large seamless network. Wi-Fi 7. Wi-Fi 7, officially known as 802.11b, launched in 2024 and earned the designation EHT, which stands for Extremely High Throughput. This name is entirely appropriate because Wi-Fi 7 can reach maximum speeds of 46 gigabits per second, which is genuinely insane when you consider that Wi-Fi 1 managed only 11 megabits per second just 25 years earlier. The speed alone makes Wi-Fi 7 impressive, but the real advancements lie in the sophisticated technologies that enable both speed and reliability improvements simultaneously. One of Wi-Fi 7's most significant features is MLO, which stands for multi-link operation. Normally, your device can only connect to one frequency band at a time, forcing you to choose between the long range of 2.4 GHz or the higher speeds of 5 and 6 GHz. With MLO, Wi-Fi 7 devices can connect to multiple frequency bands simultaneously and combine them together. This means you get the extended range of 2.4 GHz plus the higher speeds and lower congestion of the 5 and 6 GHz bands all at the same time. No more choosing between coverage and performance. Wi-Fi 7 also introduced 320 MHz ultra-wide bandwidth channels, which are twice as wide as previous Wi-Fi standards. These wider channels allow significantly more data to be transmitted in each signal. Additionally, Wi-Fi 7 uses 4K-QAM technology, which packs even more data into each transmission. Another innovation called multi-RU puncturing helps stabilize connections by finding and using clean portions of the signal spectrum when interference occurs, rather than disconnecting and reconnecting the entire network like older standards did. Of course, all these advanced features make Wi-Fi 7 routers considerably more expensive than previous generations. For most regular users, Wi-Fi 5 or Wi-Fi 6 remains more than sufficient for daily activities like browsing, streaming, and video calls. Wi-Fi 7 really targets tech enthusiasts, high-end gamers, professionals working with massive files, and environments running dozens of connected devices simultaneously. Now here's something interesting. You might have the fastest Wi-Fi router available, but if your actual internet connection is slow, none of this matters. Your router is only half the equation. If you want to understand how internet speeds themselves have evolved from dial-up to fiber optic, check out my next video covering every internet speed evolution.